thank you very much for the kind invitation to invite me here as well. So I'm testing out some new material on you all today. This work, which has actually also been done in collaboration with Paola Testa, who's at the Smithsonian Astrophysical Observatory in Lockheed, has been a few years in the sort of gestation now and is hopefully, fingers crossed, very nearly ready to be submitted to a journal. And we're interested in looking at how one might go about looking for signatures of heating in the corona in transition region radiation, because looking for signatures of heating in the corona turns out to be extremely difficult for reasons that I will try to explain. And so we thought, well, perhaps we'll have a little bit more luck in the transition region, thanks to the advent of very powerful new instruments, in particular the Interface Region Imaging Spectrometer, or IRIS, as it's more cleverly known. So my talk's going to look a bit like this, and because this is a colloquium, I feel like I should actually endeavour to make some introduction concerning what the solar corona kind of is, and then talk a little bit about the physics of the corona, in particular the heating and cooling cycle, and then one or two actual signatures of coronal heating that we've been on the hunt for, but as I've kind of alluded to already, why they're actually quite difficult to spot, and what has actually led us to looking for signatures in the transition region instead. So I'm going to talk about some of the properties of the transition region spectral lines and atomic processes in the transition region that we're needing to consider in this context. And then I'm going to move on to a numerical investigation that has formed part of the work that we've been doing together, and one or two of the results that we found, and then I'll wrap everything up. Do feel free to ask questions and things as I'm talking. I'm sure you will anyway, but that's absolutely fine. Okay, so what I like to do when I'm introducing the corona, and I hope this works, is show, here we go, is show a nice little movie of the corona that was very kindly provided by the Solar Dynamics Observatory, which is a very powerful instrument that we have for observing the corona in all its glory. So this was a what we're going to see here is a very nice presentation that's put together by media specialists at NASA using observations provided by the Atmospheric Imaging Assembly on this observatory. And we're going to see the corona in a whole bunch of different wavelengths of ultraviolet light, and we'll be looking at gas at a whole range of different temperatures as well. Now this video, I know some of you have seen it already, but this video is actually available on YouTube. It's about half an hour long actually, and obviously we're not going to see all of it because that would be a very lazy colloquium indeed from me. But I'm just going to maybe just turn this down a little bit. Comes with quite a nice soundtrack too, so it's quite nice just to listen to if you just want to kind of chill out. So here we're looking at the corona in, this is the 171 angstrom channel of the Atmospheric Imaging Assembly. So we're looking at gas that's probably formed, the emission that's formed somewhere around 600 to 700,000 degrees Kelvin. And what I just want to sort of draw your attention to mainly are these bright regions here, which contain these rather beautiful loop-like structures. The image changes, we're looking at the 304 angstrom channel now, perhaps an 80,000 degree gas. That radiation was emitted by helium-2, and we're back to the 171 angstrom channel now. We're looking at sort of iron-9 type emission here. But again, what I want to draw your attention to are these rather beautiful loop-like structures where we're seeing, to all intents and purposes, the magnetic field, but being illuminated by the emitting ions that are constrained to orbit around them and radiate at their characteristic wavelengths. And these regions are, of course, what we call active regions, and they overlie sunspot regions, which are particularly intense regions of magnetic field that lie at the surface. And in the work that Paola and I have been carrying out, it's these regions that are of particular interest to us. So this is sort of my rather sort of grand overview of the solar corona. And as I said, if you're so inclined, you can find this movie on YouTube. It's called the Thermonuclear Sun or something along those lines. And it's, as I said, it's about half an hour long or so. But it's also a nice movie to run if you're maybe giving sort of a public presentation or something like that, and you can have it, running in the background while you're talking or while people are filing in or something like that. Okay. All right, so we'll just close that off.
Why is it called thermonuclear?
I don't know, someone at NASA, some media specialist at NASA decided to call it that. I have no idea why.
Specialist, but not an expert.
Yes, exactly, yeah. So thermonuclear, that's the one that they decided to call it. That's just the search term you can use if you wanted to track it down. It's also in 4K resolution as well, so if you want to give your internet connection a good workout, then it's another good one to use. So one of the sort of the key things, the key bit of physics about the sun's corona, as far as we've sort of been able to learn, is that it undergoes a heating and cooling cycle. Okay, and so I want to talk first a little bit about the first part of this, which is the heating part. And of course, the specific mechanism that leads to coronal heating is still something that's very much an open question, and I'm certainly not, in one camp or the other when it comes to this. But I'm going to use one particular mechanism that's being investigated as an example. Again, with the caveat that whether this is the actual mechanism or not, we're not sure. But as I said, I want to use it as an example of a mechanism that may possibly put energy into the corona and heat it up. There are others that I'm not going to talk about. So, that being said, whoops, I don't want to go too far. So I'm going to talk about nanoflares. And this is the idea of reconnection between bundles of magnetic field lines that have sort of been twisted up and tangled together by convective motions in the interior of the sun. And these convective turbulent motions sort of can bind magnetic fields together, and when there's some critical angle between the magnetic field is reached, then we get a reconnection process that reconfigures the field into a lower energy state, and that energy difference is perhaps released as thermal energy in some form into the plasma. And this is our sort of canonical diagram of it. What we've done is these blue lines here represent magnetic field lines. These are the coronal loops, and we've just taken a loop and kind of straightened it out. Okay, and these two sort of grey planes represent sort of one foot point of the loop, and this plane represents another foot point, and 2L here would be the length of the magnetic field line. Okay, just for the purposes of illustration. And then we have the parallel direction along the field line and the perpendicular direction across the magnetic field. Okay, so we have these foot point motions due to surface convection that sort of twist and tangle these field lines. They kind of braid the field around each other, and then where you develop a sort of a significant where the field line sort of becomes significantly kind of misaligned, or you get a strong curl, then current sheets start to build up between them. Basically, the idea of this is it increases the perpendicular component of the field, and then once some critical angle is reached between the perpendicular and the parallel components, as the energy stored in the field increases, or in particular the stress component of the magnetic energy increases, then that's, as I said, at some critical angle, then that energy can be released as thermal energy, perhaps kinetic energy of accelerated particles and so on, that is somehow dissipated into the plasma as heat. Parker's estimate was around 10 to the 24 ergs, which is where the term nanoflare came from, as a billionth the energy of a flare. Now we really consider this to be a sort of a spectrum of energy. And yes, Yoda.
Does this model have the magnetic field in the same direction for all of these lines, or can some of them be in revert?
Well, you could think about a sort of a range of polarities here if you wanted to, but or you could just think of this as a kind of a zoom into a bundle with one polarity here and one polarity here. The sort of the image it gives, the sort of the mental image it gives you the same sort of physics. So once you have the reconnection take place, the